Everyone, my name is John Frensley, and today we'll be going over the AP Calculus free response from 2023. This video is provided to you as a free service by World's Finest Physics, which is my company. What do? We do professional development for physics teachers and math teachers, and we also do some private tutoring for students. So I wanted to tell you a little bit about those things really quickly here. We have a professional development workshop for physics teachers coming up in July, and also one for math teachers. And both of them are going to have something in common: increase student engagement through lots of hands-on activities. Hands-on activities that are easy to come by in terms of materials, but things that can really turn your class into the class where students are learning with a lot of toys that you can buy from Dollar Tree, sports balls, things that you would normally throw in the trash, like soda bottles. So navigate over to findphysics.com, and you can either click on physics teachers or math teachers, and you'll see links to the session agendas, and you'll see, the increasing student engagement with hands-on activities. For the math one, lots of competitive math-based games where students attack each other with slope-intercept lines, or games where students have to use ellipses to outwit the other person, or geometry or vectors, or boxing with complex numbers, things like that. So we're going to learn about that. We're going to integrate a lot of cross-curricular skills in the math one. Physics teachers also do this, but we're gonna look at improving student understanding through writing and things like that. And then in both cases, we're going to look at better remediation techniques. And if you're interested in private tutoring, we provide online through Google Meet private tutoring in these kind of subjects. So just go to findphysics.com. That's PHINE, find-physics.com, and explore around. Reach out to me through the contact page there, and I'd be happy to hear from you. All right, I want to give a couple of shout outs here. One is to the College Board. Thank you so much for making these tests. And also to my favorite restaurant, Golden Corral. Thank you so much for the delicious food, and thank you for not telling us where it comes from. All right, so here we go. This first one, number one, was common to both AB and BC calculus. A customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differentiable function, F, gallons per second. T, seconds after the pumping began. Okay, that doesn't have a double entendre there at all. Okay, and we've got some values in the table. Luckily, what they're not going to show us is the table of values of how much the gasoline costs. Numbers probably can't fit in these little boxes anyway. All right, interpret the meaning of the integral f of t dt in the context of the problem. Okay, so I'm going to go ahead and do that right here. So I'm going to say integral 60 to 135 f of t dt is the amount of gasoline pumped for between t equals 60 seconds and t equals 135 seconds, right? Okay. Using correct units, so it's the amount of gasoline in gallons. Okay, I feel like if I'm going to put the units down, I'm going to underline that, right? Okay, using a right Riemann sum with 3 subintervals. They have never they've never told you the subintervals before. I've never seen that on a calculus exam. Are we getting dumber? We have to be told the subintervals? You said from 60 to 135, and you tell me 3 subintervals. You don't think I can figure that out myself? Oh, well, whatever. Oh, this is the yes calculator part. I should probably have my calculator out, because heaven forbids I don't know how to do freaking basic arithmetic, because once you start doing calculus, for some reason, the arithmetic just stops working for you. Okay, so let's see what I got going on here. So it's a right sum. So what I got to do is I'm just going to tell you right now, I generally draw a picture. That really helps me, and you'd be surprised how much it might help your students also, to just draw a picture so that they understand what the flip you're trying to talk about here, right? So this is going to be 0.1 high, 0.15, 0.1, and 0.05. The right sum means that for each subinterval, I am going to be looking at the right side value. So meh, and then meh, and then. Okay, so there you go. So what's going on right here? We've got 0.05. That's the, the 0.15. That's the height multiplied by the base of 30. I can't do that in my head. Is it four? It's 45 or 4.5. It's some kind of something with a 4 and a 5, but you think I'm figuring that out in my head. All right, 4.5 gallons right there, right? Okay, and then let's see. We've got 0.1 by 30, so that's 3 gallons right there. Okay, and then this would be 0.05 multiplied by 15. Okay, I can't do that in my head. I probably can, but I don't feel like it right now. Okay, really? 0.05 times 15? Is that really all there is? Okay, so that's going to be 0.75 gallons, right? Okay, so it's going to be 4.5 plus 3 plus 0.75 gallons. No, I'm not going to try and do that in my head. Plus 3 plus 0.75. I just don't feel like it right now. 8.25 gallons. Okay, so 8.25 gallons. So you've got your really, really tiny Kia that only needs 8 gallons of gas in its tank right there. Okay, great. Must there exist a value of C between 60 and 120 where the derivative equals 0? Does there have to be between 60 and 120 a place where the derivative equals 0? Well, here's what I'm going to say about that. I'm going to say yes, since f of 60 is equal to 0.1. There it is right there, f of 60.1 gallons per second, and f of 120 equals 0.1 gallons per second. Then the average value of f prime of t on 60 to 120 is 0. Wait a minute. Hold on a second. Yes. Okay. The average value of f prime is 0 gallons per second squared. Now, I don't think you have to put all these units on the AP Calculus exam, but I'm also a physics teacher, so you know what? I put units on things, right? Okay, so gallons per second squared. Now, since f of t is differentiable, I would love to get that word differentiable into a triple word score in Scrabble. Since f of t is differentiable, right? F prime of t is continuous, so the value of f prime of t must equal the average of f prime of t in the interval 60 to 120. Now, do you have to write all this on AP Calculus? Probably not, but I'm also doing this to help people who might be like, I don't know how to answer these questions, right? Okay, so the rate of flow of gasoline in gallons per second can also be modeled by G equals this monstrosity between 0 and 150. Using this model, find the average rate of flow of gasoline over the time interval 0 to t to 150. Let me just tell you right now, it's a good thing they didn't say the average rate of flow of gas, because they said the average rate of flow of gas, it made me think about eating at Golden Corral. Let me just tell you that right now. Okay, so the rate of flow of gasoline can be modeled by this. You find the average rate of flow. Okay, so what do I know about average? Well, what I tell my students is that the average of a function is equal to the integral over the interval. The integral over the interval. Okay, so the average rate of flow of gasoline, okay, all good. So I'm going to take an integral 0 to 150, all right, t over 500 cosine of t over 120 squared dt, and then I'm going to divide that by the interval 150. All right, so that's the setup right there. So now I'm going to use a calculator to evaluate the integral, right? Okay, so let's go ahead and do that. So I'm going to turn this system thing on, math number 9, 0 to 150. Okay, let's make sure my calculator's in radians, okay? Remember, if your students take physics, it's very likely that their calculator may be in degrees. So always before the AP exam, tell your students to set their calculator to radians. Now, you might say, well, it should always be in radians. Well, you never know. I use X instead of T because I don't care enough. 14 so the integral comes out to 14.4 basically. Dividing that by 150 is going to give you 0.9096. So basically 0.096 gallons per second. Okay. So yeah, okay, that's a decent flow of gasoline. All right. Using the model G defined in part C, find the value of G prime of 140. Interpret the meaning of your answer in the context of the problem. Well, they told me that G was this nightmare, T over 500. Okay, cosine of T over 120 all that squared. Okay, right. And so, frankly, G prime of 140, is there any reason why I can't? I mean, this is a yes calculator part of the exam. Is there any reason why I can't just go to math, numerical derivative with respect to X? I'm going to make this with respect to X. And then I'm going to say T over 500 and then cosine of T over 120 squared and then that. And then at X equals 140. Is there some reason why I can't do that? Okay, so it looks like it's about negative 0.005 basically. How are you supposed to round on an AP Calculus exam? I think they want you to do like 3 decimal places or something like that. Well, 3 decimal places here gives you 14.4, but down here it's 4.005. Oh, it is 0.005. That is 3 decimal places because, of course, what I'm thinking significant figures, right? So I'm looking at the 3 significant figures is 491, right? But that's not how you math people do it. You just say decimal places. This is going to be in gallons per second squared, right? And so is this. This is the rate at which the rate of flow of gasoline is changing, right? So in other words, the flow rate decreases by negative 0.005 gallons per second every second, right? Like I'm going to spell it the frick out, right? Okay, important rule when you're talking about AP Calculus, it goes to AP Physics also, is that there's no problem talking to the reader like they're a moron. Like I'm going to spell this shit out for you, right? Like you're the dumb, because there's going to be a relationship between your student and the reader, and someone's the moron in that relationship. So either your student has to spell it all out like the reader's a moron and has to be taught calculus, or you run the risk of your student being thought of as the moron by the reader, right? So I'm just going to tell you, somebody's a moron. So tell your students to talk to really, the reader doesn't need to know all this. Well, maybe they do, okay? Like, make it clear that you know what you're talking about. You could have done this the old-fashioned way. You could have been all like, okay, well, 1 over 500, that's the derivative of this, cosine of T over 120 squared, right? Then plus T over 500, then the derivative of this, which would have been negative sine, and then the inside stays the same, okay? And then we have to multiply by the derivative of the inside, which is 2t over 120, and I'm not simplifying that. You think I'm simplifying that? Then I have a bridge in Brooklyn to sell you. Okay, Stephen, this is the AB question. So this is still a yes calculator, but this is the question that only appeared on the AB exam. Now, this is the part where I'm going to tell you. I have not actually seen these questions in advance. I only saw them enough so that I knew which ones were on the AB and the BC, or which one was just AB and which one was just BC. Not actually worked them out yet, okay? So Stephen swims back and forth along a straight path in a 50-meter long pool for 90 seconds. Stephen's velocity is modeled by this awful function that's going to require a calculator. Well, yeah, it's going to require a calculator for me to do, especially if I have to take an integral. That requires integration by parts. It's not an AB topic, right? And Stephen, what is this? Meters per second. So Stephen can swim pretty fast. He can probably commit sexual assault and get off just because he's such a good swimmer. Like, okay, there you go. Find all times T in the interval 0 to 90 in which Stephen changes direction. Oh, well, it's when the velocity changes sign. Again, I'm going to write that out like the reader's a moron. When V of T changes sign, Stephen changes direction. Okay, so let's see what we're going to do here. We're going to do a big little I equals here. And we're going to do a little, oh my gosh, why does it take so long to do anything in the freaking calculator? E to the minus 0.02 x or t or whatever you want to call it. Doesn't really matter anymore. Pi over 56 times x. Okay, all good. All right, now I'm going to set my window. My guess is that I'm not going to need my y's to be any more than 2.38, but it sounds like, what was the interval? Up to 90. Let's just go up to 100 for the heck of it. Okay, that's for good measure. Okay, so how many times does the velocity change sign? Ring. And that's it. Okay, well, let's go ahead and calculate a zero. Okay, left bound, right bound. Okay, is a 56. Serious? Why did I have to do that on the calculator? Okay, shame on me. And why do the lights turn off in this classroom? Okay, I have to walk around the classroom because the lights turn off if I don't move. Okay, I'm not moving like Steven is. Why'd I even do that? Shame on me. Okay, well, it's t equals 56 seconds when sine of pi over 56t, I'm legitimately ashamed of myself that I had to do that in the calculator, is 0. I told you I haven't seen this already, right? Now we know that e to the negative t is not 0, ever. Okay, find Steven's acceleration at time equals 60 seconds. Show the setup and indicate the units of measure, meters per second squared. If your students have been in physics class, they should be able to know that acceleration is in meters per second squared. So we're going to do d velocity, d time. So what I can do is I can, well, you know what's nice? I have the function already here in y1. So I'm going to do function numeric. I'm going to do numerical derivative, and I'm going to do a derivative with respect to x rather than time. But I'm going to push vars, y vars, function, y1. And if I do that, then it's just going to plug in this function right there for me, which is super convenient. And then if I plug in 60, you get negative 0.036, okay? So you're going to get, and evaluated at t equals 60 seconds gives, what was it? Negative 0.036 meters per second squared, right? Okay, now, if you wanted to do this the old-fashioned way, then you would have to take a derivative. You'd have to say something like dv dt. Okay, so let's look right here. So let's keep the 2.38 e to the minus 0.02t, and we're going to multiply by the derivative of the next piece, cosine pi over 56t times pi over 56 from the chain rule. Then we have to add to that the derivative of this monstrosity. So that's going to be negative 0.002 times 2.38 e to the minus 0.02 t. Okay, so that's the derivative of the first part, and then the sine, the second part, just stays perfectly good on its own. Okay, so you could do all that. You could plug in 60, all good, plug in 60. But what does it say here? Is Steven speeding up or slowing down at time t equals 60 seconds? Give a reason for your answer. Now this is the part where the physics teacher in me is going to come out, because this is what I teach my students. I teach my students that if an object is speeding up, then velocity and acceleration have the same direction, which would be the same sign. And if an object is slowing down, that means that velocity and acceleration are in opposite directions, which means they have opposite sign. Okay, so we see that the acceleration is a negative. But what is the velocity? Well, let's check it. I think I already know the answer because I'm going to plug in 60 and I have a negative here also. I'm going to say that v at 60 is itself negative 0.160 or whatever kind of thing. And the acceleration is negative 0.036 meters second squared, meters second here. Okay, so since v and acceleration are both to the left, okay, the Steven is speeding up. Another way you could say is you could say that the velocity graph is trending away from 0. If velocity is headed away from 0, either positive or negative, then the object's speeding up. All right, so there you go. Find the distance between Steven's position at time 20 and his position at time 80 seconds. Show the setup. Okay, so position is the integral of velocity. And the distance between two positions, delta x, is going to be the integral of v dt. We're going to go from 20 to 80, 20 to 80, okay? So we're going to take the integral from 20 to 80 of what is this that I'm going to integrate here? Okay, 2.38 e to the minus 0.02 t sine of pi over 56 t dt, right? Okay, so good for me. I already have freaking functions or a freaking calculator, right? So I'm going to take that. I'm going to go to freaking numerical integration. Okay, so I'm going to freaking numerically integrate from, where was that again? 20. When was that? I really should say. Time equals 20 to time equals 80. Okay, so the function is stored in y1. So I'm going to highlight this space right here. And I'm going to go to vars, arrow over to y vars, choose function, and y1. It's pretty convenient if your students can master this idea, because notice I would have had to type this entire sack of crap into a numerical derivative and then into a numerical integral. That takes time. That's precious time on AP exam, right? Okay, so here we go. 23.38 meters. Are we going to get down to the millimeters? Like, seriously, okay? Is it that precise? You mathematicians are this precise that you can get down to the millimeter, like precision of where Stephen is, okay? Like, anyway, so there you go. Do I have to do 3 decimal places? I'm a scientist. I'm thinking significant figures here. Find the total distance Stephen swims from 0 to 90 seconds. Show the setup for your calculations. Oh, now this is the place where you can get confused. Distance is the integral 0 to 90. It said 0 to 90, okay, of the absolute value of velocity dt. The absolute value of velocity dt, right? So that's integral 0 to 90 of the absolute value of 2.38 e to the minus 0.2t, 0.02t sine pi over 50. So it gets really annoying to like keep writing the same function over and over again. And just wait until you read these. If you're not an AP calculus reader and you've taught AP calculus maybe a couple of years, maybe 3, put in for it, right? It's grueling work, but it is good work. It really helps you become a better teacher. But man, you think the students get pissed at these questions? Just wait until you read them. Okay, so what am I going to do? I'm going to go back to this setup right here. Only this time, I'm going to work on my abs today. Okay, so I got my abs. So I have my absolute value bars there. I'm going to do my y1 right there like I always did. Vars, y vars, function y1. Okay, and then I need to make sure that I'm going from 0 to 90 right here. Okay, so we're going to do an ab workout here with our absolute value. And Stephen goes, wow, it's taking a long time. All right, here we go. I'm going to be collecting my Social Security by the time this thing finishes up. You're kidding me. Okay, 62 meters in 90 seconds. Is that even actually good swimming? I have good swimmers, but they're not very bright, so they would not be in AP Calculus or in AP anything. Meters. Okay, so there you go. All right, so there you go. That takes care of that. Now, why did I print out that same question twice? Oh, no, that was the question I just did. Never mind. All right. Okay, so after Peter Benchley finished writing JAWS, he went to write questions for the AP Calculus BC exam. Okay, so this is the BC question that was on the yes calculator part. After this, I have to get rid of my calculator, and I'm not thrilled about that. Okay, from 0 to pi, a particle moving along the shark's fin show that its position is xy, where x is not explicitly given, thanks for nothing, and y is 2 sine t. Okay. It is known that dx dt equals this horrible nightmare. At time t equals 0, the particle is at position 1, 0, glorious. Find the acceleration vector of the particle. The acceleration of the particle is literally d squared x over dt squared, d squared y over dt squared. Okay, so how are we going to do that? Well, if dx dt is e to the cosine t, then d squared x over dt squared is, okay, the derivative of e is himself. The inside, or the sky, at least stays the same. But then I have to multiply by the derivative of what's inside the exponential, which is up in the sky, negative sine of t. Now, we were told that y is 2 sine t, so that means that dy dt is 2 cosine t, easy, and d squared y over dt squared is negative 2 sine t. Yay! Okay, so I'm going to say the acceleration vector is, you use this angle bracket stuff, you people, okay? I just use the normal ordered pair notation for my components. Okay, so negative sine t times e to the cosine t, and then negative 2 sine t, and off to the races we go. That was part A right there. All right, for 0 to pi, find the first time at which the speed of the particle is 1.5. Show the work that leads to your answer. Okay, now speed is the Pythagorean theorem of the velocity components. The velocity components are dx dt and dy dt, which in this case would be, what did I have? Oh, e to the cosine t and 2 cosine t. Okay, that's the velocity. Speed is the Pythagorean theorem of this crap. So we're going to take the square root of e to the cosine t all squared plus 2 cosine t itself squared. I am not going to simplify this, but I am going to graph it in my graphing calculator. Okay, so integral of e to the cosine t, or x as it happens to be in this case, plus 2 cosine x, or whatever it is, t, all squared. Now, this is from 0 to pi, so I'm going to zoom 4, and I think all I want to do is I might want to zoom trig. Is that a smart choice? I don't know. I'm not very familiar with the zoom trig. You know what I'm going to do is I'm going to not do that. I'm going to go from 0 to that. Why is it not 2 pi? That's weird. Not 2e. Okay. X scale. Yeah, let's go by pi over 2s. That sounds smart. Okay, and then min to max. Yeah, it sounds good to me. Oh, wait a minute. I didn't mean to do that. I meant to do just pi. Okay, so once again, I did not actually work these out before I started doing this. Okay, so these are pi over 12s. Okay, so 1, 2, 3, 4, 5, 6. Oh, wait a minute. I'm looking at this at a specific time. Oh, wait a minute. No, I'm looking for when this is 1.5. Okay, so let's also graph 1.5. Okay, let's see. Okay, so now we're going to find the intersection of these two curves. And I know there are other ways to do this. You can use like a equation solver and kind of crap. But you know what? I just want to get this over with. I'm doing this as a public service. Is that the actual intersection? That you're not serious, are you? That doesn't feel like the intersection. Let me go back again and try that again. Okay, we're going to intersect. First, second curve. Guess. I'm not going to guess. You guess. Your job. It seems like the same point I was just at. That seems really weird. Okay, well, let me just make sure that I'm not crazy here. Okay, so let's go here, here, here. Will it bring me back over here? Yeah, it does. Okay, 1.25. Okay, so set the speed equal to 1.5. Is that what it said? Yes, in the calculator, and solve. And the time we get is 1.254. Is there any units on this? No, why would there be units on anything? It's a calculus exam. Okay, I can't stand to write t equals that without units. That really is like going to bother me for the rest of the day. I'm going to lose sleep over it, right? I'm probably going to get home and kick my dog over the fence just because there's not units in this problem. Okay, find the slope of the line tangent to the path of the particle at time equals 1. Find the x-coordinate of the position of the particle at time equals 1. Show work. Okay, let me think about this really quick. Now, the slope of the line is dy dx. So the slope is dy dx, which will be dy dt over dx dt. So we know that dx dt is e cosine of t, and dy dt was 2 cosine of t. So then I'm going to plug in just 1, and let's just go ahead and say 2 cosine of 1, which is not a prime number, e over e to the cosine of 1, which is really not a prime number. And then you get this, which is like somebody's phone number. Try dialing this, 629-530-1096, with somebody watching this video. What if that was your phone number? What are the odds of that? It's so crazy. Okay, 0.629. I guess if I'm only going to do 3 decimal points, it would be the decimal place 630. Okay, so that's the slope. Now, the x-coordinate is a little bit difficult because what were we given? We were given the dx dt, not the x. It says is not explicitly given, okay? So there you go, x-coordinate. So, oh, I know, you should do this. Delta x is the integral of dx dt dt. We're going to go from time 0, because we know that time 0, to time 1. We're going to go from 0 to 1. And what is this going to be? This is going to be x at time equals 1 minus x at time equals 0, the fundamental theorem of calculus. So x at time equals 1 is what I would like to know. The x at time equals 0 is right there. Let's take this integral. Okay, so the integral from 0 to 1 of e to the cosine t dt, it will probably take my calculator several minutes to do. So let's see, 0 to 1 of e to the cosine t x, whatever. I don't honestly give a crap anymore. Oh my gosh, it got done really quickly. How does that make any sense? 2.342 basically. So let's add 1 to that. And the position at t equals 1 is 3.342 meters. Okay, so there we go. Okay, find the total distance traveled by the particle from 0 to pi. Show the setup for your calculations. Okay, so distance. Did I not just say that on a previous problem? Okay, here, the distance is the integral of the absolute value. That's in one dimension. Notice that's actually the integral of v squared. Here, it's also going to be the integral of v squared, vx squared plus vy squared dt. So you notice the distance is actually the same thing, right? This is like horizontal because Stephen was going back and left and right in the pool, and there was no y velocity, like he wasn't flying or anything like that. He's not freaking Peter Pan or whatever. So there's no y velocity. He's just going back and forth in the pool. And as long as he's swimming in the pool, he's not sexually assaulting anybody, right? Okay. But now what do we got going on here? We're moving along the shark's fin, right? Okay. This is like my mood. Okay. So what do? I'm gonna take my Quaaludes. My mood goes up and then it precipitously drops, right? Okay. Now the lights turned off and now I'm depressed because I have to walk around the room. This is so undignified. Can I just tell you that right now? Like I should be treated better by the light system than this. Okay. So we're gonna go from 0 to pi. 0 to pi. What was Vx? That was dx dt, which is e to the cosine t squared. And then we just had it right here. It's just this. 2 cosine t squared dt. Is that already stored in my y equals? Yes! Thank goodness. That means I don't have to really do a lot of work here. I have to go to function numerical integration. I got to go from 0 to pi. I've got to do y1 where it's stored using my trick I keep showing you. And then this is going to wind up being 6.035 meters. Okay, so there you go. That was the shark's fin. Now we go to the no calculator portion, which is my favorite. Kind of like going to Golden Corral, the throwing up afterwards is my favorite, right? Okay, it's not the case. So a bottle of milk is taken out of the refrigerator and placed in a pan of hot water to be warmed. Oh, I guess this is taking place at Golden Corral. Who knows? The increasing function m models the temperature of the milk at time t, where m of t is measured in degrees Celsius and t is the number of minutes since the bottle is placed in the pan. M satisfies the differential equation. That at time equals 0, the temperature of the milk is 5 degrees Celsius. Thank you for actual units for freaking once. And then it can be shown that m is less than 40 for all values t. I have no idea why they had to tell that to me. I could have told you that 40 was the asymptote just by looking at this. Why are the students like just dumb now that they have to be told all this information? Okay, here's a slope field. It looks like the back of my cat whenever I approach. Okay, so here we go. The slope field is shown. Sketch a solution curve to the point. Okay, here we go. So I'm going to try and make this really smooth here, okay? So we're going to make it really smooth. We're going to try and go along with a little porcupine quilt here, okay? So we're going to make it a little porcupine quilt, okay? And we're just going to go right along with that, okay? Try and make it smooth. Make it smooth as a baby's butt. Okay, and then we can see the asymptote right here. Okay, some asymptote asshole told us that this was the asymptote, but we didn't have to be told it's the asymptote because anybody with 2 halves of a functioning brain can figure out that that's a fucking asymptote. All right, so there you go. That's a solution curve. Use the line tangent to the graph of m at time 0 to approximate m at 2, the temperature of the milk at time 2 minutes. Okay, so what do we know? We know dm dt is equal to 1/4 40 minus m. We know that m at 0 is 5. So then I'm going to say at time equals 0, dm dt is equal to 1/4 40 minus 5, which is 35 over 4, which sucks because you can't reduce that. All right, now time for a line. Y minus y1 equals slope x minus x1. Now, for the sake of this problem, it's really m minus m naught, the initial value of m, slope t minus t naught, if you're going to use the exact correct letters here. So m is what we want to approximate. M naught, which I pronounce like I'm from Brooklyn for some reason. I don't know. Anyway, 35 over 4. The t is, what was the t? 2. The t is 2. The initial time is 0. So then I'm at least, oh gosh, okay, m minus 5 equals 35 over 2. I don't know what the frick that is. Is that 17 and a half? So then I'm going to add, it's going to be 22 and a half degrees Celsius or something like that. That's my estimate. Okay, so there we go. Write an expression for the second derivative of this stuff. If dm dt is 1/40th times 40 minus, I'm totally, 1/4, I mean, and I'm just going to distribute, can I just tell you? Okay, so 10 minus 1/4 of m. Then the derivative of the derivative is the second derivative. Okay, so we take a derivative of the derivative and we get the second derivative. The derivative of 10 by himself, adding or subtracting, is 0. Okay, and then the derivative of m is dm dt, which is funny because I already know what dm dt is. It's that. So d squared m over dt squared is going to be negative 1/4 times that shit, which is negative 1/16, because 1/4 times 1/4 is 1/16, 40 minus m. Okay, now, use the second derivative to determine whether the approximation from part B is an under or an overestimate. Okay, when t equals 0, this is part B, by the way, I should probably label this part A also. When time equals 0, m is equal to 5, and d squared m over dt squared is negative 1/16 times 35. So negative 35 over 16, which is negative, right? Okay, so this means the graph is concave down. Oh my gosh, I didn't know that. I would have never guessed this is concave down. Shitheads. Anyway, okay, this means the graph's concave down. So any linear approximation will overestimate the value of the original, or the, I'm going to say the actual function, since the function curves downward, you wombat. Okay, so I'll put a comma because you're addressing the wombat. All right, so here's your function right here. He's got the same look on his face that I have on my face. And so you draw like a tangent line here. If you go over here, overestimate. If you go over here, overestimate. If you draw a tangent line here, go over here, overestimate. Go over here, overestimate. So that's a feature of second derivative being negative, is that local linear approximations will overestimate the true value of the milk is actually less than 22.5. Oh, that was part C. Oh, this is B, and then this is C. I don't know my letters. Okay, can I just tell you? I start with B anytime I say my letters. Okay. Use separation of variables. Okay. Find the particular solution. All right, so here's separation of variables, D. So D milk, D time is 1/4, 40 minus M. So I'm going to bring the DT up and the 40 minus M down. Yes, that's how it's going to go. DM, and then the 40 minus M goes down. The 1/4 DT is going to be here. Now we're going to drop a big old crowbar into the middle of this disaster. And then this is going to become negative natural log of 40 minus M. At this point, when your students are taking a calculus exam, they should be able to integrate the natural log in their head. I hope that they'll still have to do U sub. Here's the easy way to do it. The easy way to do it is just say, can you make the numerator the exact derivative of the denominator? The derivative of the denominator is 40 minus M. The derivative of 40 minus M is negative dm. This is regular dm without the negative. It's positive dm. Let's multiply by a negative, and then we can multiply by a negative also. Or you know what you could do is just not do that and bring the negative over here. That's a feature of equations, is that equations, you can do the same thing to both sides. So without doing u and du, I just make the numerator the exact derivative of the denominator, and I get natural log of 40 minus m. Okay, on the other side, I'm going to get negative 1/4 t. And now I'm going to tell you the way that I do these things. The way I do these things is I will put a plus c, and then I'm going to solve for the m. That means I'm going to e up the other side. Okay, so 40 minus m is equal to e to the minus 1/4 t. The plus c becomes a times c. It's a different c. I know that you math people are really precise, and you want to probably say this is C1 and this is C2 because they're different C's. I'll do that because I love you, but in my class, this C, nobody freaking knows what the C is. Who even cares? All right, so now I'm going to switch colors for this because I switch colors anytime I do this with my students. I teach the calculus-based physics, so we do a lot of these. I switch colors whenever we actually plug in the initial values. M equals 5 at t equals 0, right? So 40 minus 5 equals C2, e to the negative 1/4 times 0. E to the 0 is 1, so that means that C2 is 35. So then switching colors back, now that I know the C2, 40 minus m is equal to 35, e to the minus 1/4 of a t. So then if you flip it around, m equals 40 minus 35, e to the minus 1/4 t, and that is your solution right there. With the initial, I think I did it. I think that's it right there, folks. Okay, that was A, B, and B, C, and you notice I didn't use a calculator. All right, this would pass for a work of art nowadays, a triangle and a circle, and that's all you need, right? That's modern art for you. Okay, let's make sure we're not stupid. We're looking at the graph of the derivative of some function. All right, the function f is defined on the closed interval, and the function that I can't see has 1 as its value at f at 2. The graph of f prime consists of 2 line segments in a circle. Does f have a minimum, maximum, or neither at x equals 6? Well, here's what I'm going to tell you. So here's my statement here. To have a relative minimum, the derivative, which is f prime, must change from, I have to draw it every time. From negative to positive. Okay, so you have to have a negative to a positive derivative, but to have a relative maximum, you need the derivative to change positive to negative. Okay, so it's going to look like that, right? Okay, all good. All right, so what happens at 6? You go from positive to positive again. So f prime changes from positive to positive at x equals 6. So neither a max or a min. It's actually an inflection point, if you're wondering. Inflection point. Okay, so all good. B, on what open intervals is the graph of f concave down? Is the graph of f concave? So we're going to say f is concave down if f double prime is negative, okay? And so what is f double prime? F double prime is the slope of f prime. So when is the slope of f prime negative? So I'm just going to visit some intervals. Oh, open interval. Looks like -2 to 0. -2 to 0, open interval. Don't include the endpoints. Oh, that's a positive second derivative because the slope of the first derivative is positive. Oh, looks like 4 to 6, we have a negative second derivative because the slope of the first derivative is negative. Find the value of this awful limit. Okay, well, I don't really want to. First of all, I know your students are going to jump straight into some limit techniques. I would strongly encourage your students to think twice about that and just check that it is an indeterminate form. Okay, so we were told that f at 2 is 1. So 6 minus 3 times 2, that's not looking good. That's 0 on the top. And then 25 minus 30, 4 minus 10 plus 6. I don't know what I was thinking trying to plug in 5. That's also 0, so 0 over 0. Okay, well, limit x approaches 2, this is part C, of 6 f of x minus 3x over x squared minus 5x plus 6. Why don't we use the hospital rule, okay? So L'Hospital's rule, okay? I don't know how to spell L'Hopital, actually, and you know what? I don't care, okay? So there you go. So what we're going to do, we're going to take the derivative of the top, okay? 6 f prime minus 3, and we're going to take the derivative of the bottom, 2x minus 5. Okay, f prime's value is 0. So I'm going to get 6 times 0 minus 3 over 2 times 2 minus 5. That is negative 3 over negative 1, so you get 3. That's what the limit evaluates to. Yay. Okay, so 3. Put a box around it, maybe tie it with a ribbon and stuff like that. Okay. D, find the absolute minimum value of f on this entire closed interval. Justify your answer. Okay, so I know that I need to try the endpoints, and I know I need to try all relative minima. What do I know about a relative minimum? I said that it's when the derivative goes from negative to positive. So the derivative goes from negative to positive only at negative 1. So what I'm going to do now is I'm going to make a table for this function, x and f of x. I'm going to try the endpoint, I'm going to try the relative minimum, and I'm going to try the other endpoint of the interval. Let's see how I do here. Oh, and you know what I'm going to do is I'm going to put 2 in there just for good measure because we were given this information, f at 2 is 1. Okay, so how am I going to find the function values? To find the function values, what I'm going to do is I'm going to take integrals. The function at 2 minus the function at negative 2 is going to equal the integral from negative 2 to 2 of f prime of t dt, or however you want to say that. So let's go ahead and take some areas here. The red area is 2 by 2, so that's 2 for a triangle. The green area is negative 2. It's the same shape. The pink area is going to be negative 1, and the purple area is going to be positive 1. Now I have to do this, which I really don't want to do. Okay. Oh, heavens. What is this? Okay. So the area is pi r squared. That's pi times 2 squared, which is 4 pi. But that's the area of the entire circle. So this would just be pi because it's 1/4 of a circle. This area is also pi. And the area of this entire thing is 4. So this blue shaded area is 4 minus pi. This blue shaded area is also 4 minus pi. Okay, so how am I going to take the integral from negative 2 to 2? Let's count up the areas from negative 2 to 2. Okay, so we're going to get positive negative 1, negative positive 2. So that this whole thing evaluates to 0. This evaluates to 0. So f at 2 and f at negative 2 must be the same value, which is 1. Now, let's try it again with f at, you probably shouldn't cross that out, actually. I would actually, if I was showing work, I would not cross that out. And the reason, because you want it to be graded. So don't cross out. It's a little late now. You've already taken your calculus exam, and then now life is going to move on for you. Let's try negative 1, f at negative 1, and the lights went out again. It's the night that the lights went out in Frensley's classroom. Okay, now this time I'm only going to take the negative 1, the negative 2, and the positive 2. So this integral evaluates to negative 1. This is f at negative 1, and this is going to be f at 2, which is 1. So then 1 minus this, so this has to be negative 2. And then when I try this here, I'm just going to tell you right now, I'm going to make an argument here that this is greater than 1 because f prime is greater than 0 for 2 to x to 8. So the integral from 2 to 8 f prime of t dt is greater than 0, right? So because it's greater, then that's the minimum. Okay, the absolute minimum is at negative 1 comma negative 2 is that point right there. Okay, so I didn't move around. So that means that the lights are now permanently off, and I have to walk all the way across my classroom. I am a science teacher, so my classroom is actually 3 times bigger than any of your math teachers' classrooms, right? So that means I have to walk. You can hear it even echo, right? It's like the Royal King's Hallway or something like that. Okay, very modern art. Okay, this is an A-B only question, no calculator. The functions f and g are twice differentiable. Great. The table shown gives values of the functions and their first derivatives and selected values of x. Let h be this crap. Find h at 7. Okay, so if h is f composed of g of x, then h prime of x of x will be the derivative of f, g stays the same, times the derivative of g. That's the chain rule. H prime at 7 will equal f prime of g of 7 times g prime of 7. Here it is. Okay, so g at 7 is our f prime of 0 times g prime at, what is g prime at 7? Times 8. What's f prime at 0? F prime at 0 is 3 halves. 3 halves times 8 is 12. Whoopee. Okay, let k be a differentiable function such that k prime is f of x squared times g of x. Is the graph of k concave up or concave down at x equals 4? Well, I only know one way to evaluate a concavity, and the way that we evaluate a concavity is with the second derivative. If k prime is f of x all squared times g of x, then k double prime will be the derivative of this. We need to take the a power rule here, so 2 times f of x, then times the derivative of f, then times g, who just stood there. Okay, I just took the derivative of u, and I kept v the same. Now, this is a product rule. Derivative of u times v. Now, u, which is not changed, times the derivative of v. Okay, so k double prime at 4 is going to be 2, f at 4, f prime at 4, g at 4, plus f at 4 all squared, g prime at 4. Okay, I'm going to be making a lot of use of the table here. All right, so 2 times 4, f at prime at 4 is a 3, and the g is negative 3. The f at 4 is 4 squared. The g prime is 2. I can't do math. 8 and 9, negative 72. God, that's right. All right, and then 32. Since k double prime is less than 0 at x equals 4, k is concave down. All right, let m, we're just going to go through the whole alphabet here. All right, let m be the function defined by this crap. Find m at 2. Why do I get the suspicion that this 5x cubed is just there to confuse me? So what they're really saying is they're saying, okay, m at 2 is 5 times 2 cubed, 5 times 8, 40, plus the integral from 0 to the integral of the derivative. Well, the integral of the derivative is itself, but with bounds, we have to say the f at x minus the f at 0. Oh, and by the way, this would be 2 because we're plugging in x equals 2. 2. Oh, okay, so 40. What is f at 2? 7. What's f at 0? 10. 40 minus 10 is 30 plus 7 is 37. Seems rather anticlimactic after all that. Just come up with 37. Is the function m defined in part C increasing, decreasing, or neither at time equals 2? Well, I've got one way to find out, and the way I'm going to find out is this. If m of x increases, the derivative is greater than 0. If it decreases, the derivative is less than 0. Okay, and neither of the derivatives equal to 0. So what am I going to do? I am going to say, m is 5x cubed plus the integral 0 to x of f prime of t dt, right? Well, the derivative of m, dm dx, well, that derivative is a joke, 15x squared. But then the derivative of an integral is itself. This is going to be f prime of x. That's one of the fundamental theorems of calculus. I think there are 14 of them. Anyway, so, and where are we asking? At x equals 2. So 15 times 2 squared is 60. F at prime at 2 is negative 8. So this is positive. So increasing is what it's doing. All right, that's the AB question. Now for the other AB question. Consider the curve given by this. Show the dy dx. Okay, so here we go. So A, 6xy equals 2 plus y cubed. All right, so we're going to do the product rule. The derivative of 6x is 6 times y. Then the derivative, plus. Then 6x times the derivative of y dy dx. On the other side, the derivative of 2, adding or subtracting is 0, and we get 3y squared dy dx. Okay, now let's get the dy dx here. It's 6y equals 3y squared dy dx minus 6x dy dx. Okay, let's factor out the dy dx. Oh, shoot, I didn't mean that. I meant to put parentheses here. Okay, and then we can do 6y over 3y squared minus 6x equals dy dx. And then I think we can actually factor out a 3. So that would become 2y over y squared minus 2x. Okay, find the coordinates of the point on the curve at which the line tangent to the curve is horizontal. So in other words, this is where dy dx equals 0. So that would be where the numerator, whatever, when the top of the fraction equals 0, okay? So we have the top of the fraction as 2y equals 0, so that's going to be y equals 0. Okay, I got y equals 0, great, but what am I going to do? Got to plug this back in here. 6xy plus 2 plus y cubed. Hold on a second. How do you do this? Oh, yeah, y is 0 equals, is that even possible? Or explain why no such point exists. There is no point. You can't do that. The y is never 0. You can't have a y equals 0. Why can you not have a y equals 0? Because you get 6x times 0 equals 2 plus 0 squared. That doesn't equal 0. So I'm going to say no such point exists. All right, no such point exists. Okay, find the coordinates of the point on the curve where the line tangent to the curve is vertical. Okay, so then that means that part C, the denominator. Okay, so the y squared minus 2x has to equal 0. Okay, so then you're going to get y squared equals 2x. So any point where y squared equals 2x. Okay, so let's come over here. So the denominator of the derivative has to be 0, right? Okay, so what am I going to do here? I'm going to say 6xy equals 2 plus y cubed. Okay, and then it's going to be, oh, this is going to be gross. 6x times the square root of 2x equals 2 plus y cubed. So that'd be 2x raised to the 3/2 power. That does not look, oh, maybe I could do this actually. Hang on. So we get 6 radical 2 times x to the 3/2 power equals 2 times, what is that? That's 2 radical 2 plus, I'm sorry, that's a plus. 2 radical 2 x to the 3/2 power. This might actually work out. Okay, so we bring it over. We're going to, so this and this are like terms, so subtract. 4 radical 2 x to the 3/2 power equals 2. Now, how am I going to play this game? I think I'm going to square everybody. I'm going to square everybody, so that's going to make this 16 times 2 is 32, x cubed equals square. This is 4, divide. You're going to get x cubed equals 1/8, so x equals 1/2. Okay. That's x equals 1/2. Does it say the coordinates? Okay, so if that's the coordinates, then I'm going to come over here. I'm going to say 2 times a half. So 2 times a half is 1. So y equals plus or minus 1. Am I going to regret that? I think I am going to regret it. I think it's probably only got to be y equals positive, negative. I don't think it can be negative. I think it's only got to be y equals 1. Okay, now I'm going to cheat. I'm going to open up Desmos. Okay, if you have a problem with that. Okay, so Desmos graphing calculator, right? Okay. Let's see what Desmos has to say about this. Okay. First of all, it takes forever to load. It's a nice tool, but dang. All right, 6xy equals 2 plus y cubed. All right. So there is no place where it's horizontal, and there's only one place where you have a vertical tangent line. There's no other vertical tangent lines. Okay, I was right. Okay, a particle is moving along the curve. At the instant when the particle is at point 1/2 comma -2, its horizontal positions relate increasing rate dx dt. What is the value of dy dt? Okay, so what I'm going to do now is I'm going to say 6xy equals 2 plus y cubed. And this is the way I was trained to do it. There might be a better way to do this. So I'm going to take the product rule here, 6y times dx dt plus 6x times dy dt. Okay, then over here, you're going to get nothing, and then you're going to have 3y times dy dt. Okay, so now what am I going to do? I'm going to say that the y value is -2, and the dx dt is 2/3. Okay, I'm going to say that the x value is 1/2, and the dy dt is what I want to know. Okay, we have 3, the y value is -2. Nope, that was squared, I believe. I think that was supposed to be squared. Dy dt, I don't know. Okay, so 2/3 of 4, this is -8. Plus 3 dy dt equals 12 dy dt's. So then if I bring this over, I get 9 dy dt's equals -8. So then dy dt is -8/9. All right, that's the answer I got for you. What do you want from me? All right, we're in the home stretch now. We're doing the BC questions. Okay, so what we have here is this sparrow's wing, or whatever the frick this thing is. All right, graphs of functions f and g are shown in the figure for 0 to 3. It is known that g is 12/3x. For x greater than 0, twice differentiable function f, which is not explicitly given. That's what they say to me anytime I ask for fresh food at Golden Corral. Can I just tell you? Not explicitly given. Satisfies f to the 2, and that integral equals 10. Find the area of this shaded region. Okay, so what I want to say is I want to say the green area, okay, which is this green area, minus the red area. So the area of the shaded region is green minus red. So integral 0 to 3 f of x dx minus integral 0 to 3 g of x dx. That's the area. That's the area. Okay, so that's the area. Now, what do I want to do now? This we were told was 10. Thank you very much for that. And this is going to be the integral 0 to 3 of 12/3 plus x dx. I'm going to bring out the 12, you don't mind, so it's just 1. The derivative of the numerator, the numerator is exactly the derivative of the denominator. So this is going to turn into 10 minus 12 natural log 3 plus x, taken from 0 to 3. I know y'all do absolute value bars, but it really doesn't matter for this one. So you're going to get this. 10 minus 12, let's plug in 3 to get natural log of 6. Oh, I don't have to put the absolute value bars because 6 is already positive. Minus a negative 12. Natural log of 3 plus 0 is 3. Okay, so what do I want to do? I want to say that that's 10. You don't have to simplify, but for some reason I feel compelled to. All right, it's 12. Natural log 6 minus natural log 3, which is natural log 2. So 10 minus 12, natural log 2. Is that a positive number? I threw my calculator away because I thought this is no calculator section. Is that a positive number? That should be a positive number. Minus 12, natural log 2. Yes, it's positive. Okay. Evaluate this improper integral or show it diverges. I'm pretty sure it converges because it reminds me of a p series where p is equal to 2, which is going to work. So, b, limit as b approaches infinity of 0 to b, 144, that's 12 squared, over 3 plus x squared dx, which is really limit. Can you tell how impatient I am about having to put the limit b goes to infinity? I'm a physicist. So what would I do is I would just integrate from 0 to infinity, and I would just, not even care about how you feel about what your feelings are. Okay, u equals 3 plus x, so du is just equal to dx. So I'm not really going to show that. But what I'm going to do is I'm going to raise up the power. The power raised up 3 plus x to the -1 power. I'm going to divide by the new power, so -144. And this is going to go from 0 to b, limit as b approaches infinity. Okay, so limit as b approaches infinity. I'm going to say -144 over 3 plus b minus -144 over 3. This goes to 0 because b gets huge. So I'm left with this. Oh, sheesh. 4, 12, 24, 48. Okay, that's comes out to positive 48. Okay, there you go. It does not diverge. Let h be a function defined by that. Find the value of h. Okay, so I'm taking the integral from 0 to 3 of x, okay, x times f prime of x dx. Gosh, that feels like integration by parts. So the u is the x, the du would be dx. The dv is f prime dx, so the v is f. Okay, here we go. X times f, watch out, evaluated at 0 to 3. Why do I get the feeling that that is not good? Oh, f at 3 is 2. F at 3 is 2. Oh, and f at 0 is 4. I might be able to do that. Okay, minus the integral of f v du, f dx, taken from 0 to 3. We were told that this number is 10. So to get this number right here, I'm going to do this right here. It's going to be 3 times f at 3 minus 0. It doesn't even matter. Times f at 0, so goodbye. That's a minus. So 3 and f at 3 is 2. 3 times 2 is 6 minus 10 is negative 4. All right, that was just a secretly integration by parts. All right, last one. Oh, I'm going to suck at this. Okay. The function f has derivatives for all orders. We have f at 0, f prime at 0, f double prime, and f triple prime of x. Find the fourth derivative at x. Okay, the fourth derivative at x is going to be the derivative of this. So I am going to do a product rule. So it's going to be negative 2 times f prime of x squared. That's the derivative of the first times the second. Plus the first. Now, what is the derivative of this? It would be f double prime of x squared times 2x. That's the chain rule. Okay, let me clean this up. All right, I got to clean this up. 2f prime of x squared plus, this is going to be minus, I mean to say, 4x squared. Okay, now what is f double prime of x squared? F double prime of x is negative x squared. So this will now be positive f of x to the fourth. I hope I'm doing this correctly. I don't really know what I'm doing. Okay, write the fourth degree Taylor polynomial. So T4 of x is going to be the following. All right, the function at 0, 2, times x of 0 over 0 factorial, so that's just 2. The derivative at 0, 3, times x to the 1 power over 1 factorial, 3x. The function's derivative, the function's second derivative, at 0, that'd be negative the function, that's negative 2, x squared over 2 factorial. Okay, so I plug in 0, that's negative f at 0. There's f at 0 is 2, so negative 2. Okay, so that's just going to be x squared. And then, now, how am I going to do this? At 0, oh, thank goodness for that. Okay, so there's nothing there because you plug in 0, you get nothing. And then, now I'm going to play this game. Negative 2 f prime, so f prime at 0, okay, negative 2 f prime at 0, that's negative 2 times 3, so that'll be negative 6. So f4 of 0 is going to be negative 6. Now let's do this piece. Oh, we don't have to do that piece. Okay, so it's going to be the value, negative 6 of the fourth derivative, x the fourth over 4 factorial, which is 24. So 6 over 24 gives you negative 1/4 x the fourth. That's the fourth degree Taylor polynomial at x. I hope I did that right because this is starting to give me hiccups. The fourth degree Taylor polynomial about it is used to approximate f at point 1. Given that f5 is less than 15 from 0 to 0.5, use the Lagrange error bound to show that this approximation is within 1/100,000th of the exact value of f. I am at home with scientific notation. Okay, now, what do I want to say? I want to say Lagrange error. The error is some value less than the fifth derivative at z, where this is the highest value attained by F5, okay? This right here is going to be x to the fifth, and the x to the fifth is going to be 0.1. There's where our 10 to the 15 comes from. And then over 5 factorial. So we're going to get 15 times 1 over 10 to the fifth over 5 factorial is 120. That reduces. So I'm going to make this argument. I'm going to say 15 over 120 times 1 over 10 to the fifth. This is a number less than 1 times 1 over 10 to the fifth. So this must be less than 1 in 10 to the fifth. Okay, that's my argument, and I'm sticking to it. Let G be this function. Oh, I so badly don't want to do this. I might want to quit the video right now. G at 0 is 4, and G prime is e to the x, f of x. Write the second degree Taylor polynomial for G about x equals 0. Okay, so what I'm going to say is I'm going to say G at 0 is 4. G prime of x is e to the x, f of x, which means e to the 0. Okay, wait a minute. G prime at 0 is e to the 0, f at 0, which we were told is 2. So that would be just good old-fashioned 2. Now, what is G double prime? That would be the derivative of this. The derivative of the first times the second left alone, plus the first times the derivative of the second, okay? Now, so G double prime at 0 would be e to the 0 times f of x, which is 2. We were told that. Plus e to the 0 times f prime of x, which is 3. We were told that. So that's going to be 5. Okay, so here's Taylor 2 for G. It's going to be the function's value, x to the 0 over 0 factorial, plus the derivative's value, x to the 1 over 1 factorial, plus the second derivative's value, x to the 2 over 2 factorial. And so if I dress this up, 4 plus 2x plus 5 halves x squared. Now, I am going to do a funny thing right now. The funny thing I'm going to do, and I think it's a dumb thing to do, and I'm going to do it here on camera, no matter how dumb I think it is. So what I'm going to do, I can't. I take it back. I will not do it. What I was going to do is I was actually going to try and multiply e to the x times f of x, but that only gives me G's derivative. Well, I don't know. What happens if I take 1x, 1 half x squared? This is e to the x. Okay, and then what was my Taylor polynomial for f? It was 2, 3x, and x squared. 2, 3x, and x squared. Okay, what if I multiply these, like with a window pane? Notice I'm going to ignore higher order terms and higher order terms. Okay, 2, this is going to be 3x squared. Okay, I don't think it's coming out to what I want it to be. I don't think it's going to come out to what I want it to be because, no, I don't think, well, maybe it will. Hold on. This is 3x. This is 2x. Did I miss a negative sign up here or something? Maybe I made a mistake. I don't know. Okay. And then this is going to be a single x squared. And then this is going to be a single x squared. Okay. And then all the other terms are higher than that. So I'm going to say G prime is 2 plus 5x plus, I don't even need these terms. I was going to say 5x squared. But then if you integrate, you get 2x plus 5 half x plus higher order terms. And then what were we told? We were told the function's derivative is 4. So yeah, I actually get the same thing. I get the same result. So the other result you could have done is you could have found a series for G prime and then integrated it up and tossed out every term that was higher order than x squared. Okay, I didn't know that worked. I thought it worked, but I didn't know for sure that it worked. All right, this has been a presentation of World Science Physics. I hope that you come visit my website and find out about our professional developments that we have, or if you're a student or parent, that you find out about the online help that we can give you through Google Meet. All right, thanks for sitting through this whole video.